Visible now? Hello, Prasad?
Yes, sir. Yes, sir. It's
Slide
visible.
is
It's
visible.
visible. Yeah, yes,
Yes,
sir.
sir.
Good to go.
Sorry that audio did not work, but
Yeah,
many
it's
photographs I have included in my presentation. Now, this James Webb, incidentally, is not the name of any scientist, but James Webb was a NASA administrator. And during his tenure, many important decisions as far as the space program of ES was concerned. So those decisions were taken, and therefore James Webb happens to be an important figure in the progress in space science made by USA. So in order to honor him, the telescope has been named after him. Now, when we say that we are going to explore this huge universe with the help of this telescope, let us have um, let us know what is our address in this universe. Where do we stand? So the Earth, which is part of the solar system, there are 8 planets, as we know. The solar system is part of the Milky Way, our galaxy. The galaxy, it is a collection of billions of objects, not only stars and planets, but many more objects are there, and the number goes in billions. Mind you, billion means 10 raised to 9. So 9 zeros after 1. So the galaxy, any galaxy contains billions of objects which are bound to each other due to force of gravity. The name of our galaxy is Milky Way. So our solar system is part of the Milky Way. Milky Way is part of local group of galaxies. That is further a part of some cluster of galaxies, and many such superclusters are making this universe. So there are billions of objects in a single galaxy, and there are billions of such galaxies. So that is the expanse of the universe. So our Earth has got diameter of only 12,800 kilometers, while the universe, according to the present estimate, has got diameter of 93 billion light years. This figure is in light years, while this is in kilometer. So what is so special about this James Webb Space Telescope? Now I'll be using this short form JWST, or the James Webb Space Telescope. So what is so special? Why have I selected this particular topic for today's talk? So this is the most powerful and largest space telescope ever built by human being. It is extremely sensitive. It is so sensitive that it can detect a small honeybee or bumblebee on the moon. For development, 2 decades were required. There were contributions from thousands of scientists from 14 countries, and it was mainly developed by NASA, then European Space Agency, and Canadian Space Agency. Then it has got deployable sun shield, which you must have seen in the video that I played. Then the mirror was folded when it was launched. The mirror was folded, and the reason was obvious. The mirror is a huge one, having a diameter of 6.5 meters. So that cannot be accommodated in any launching vehicle. And therefore, like origami, in origami, we fold the things. In the same way, it was a folded mirror, and it was unfolded in space. Then it is lightweight as far as previous telescopes are concerned. The most important thing about the telescope is it is infrared telescope. That is, it is going to receive mainly the infrared signals coming from space. And it is supposed to be successor to the Hubble Space Telescope, which is an optical telescope. Now let me show you electromagnetic spectrum. it shows us gamma rays, X-rays, then ultraviolet, infrared, visible, microwave, radio waves, and so on. So this Hubble Space Telescope studied the visible part of this spectrum. See, when we are looking at the space or when we are receiving signals from the space, we get waves of all these types. We get almost entire electromagnetic spectrum from coming from various objects in space. Out of that, only visible part was received by Hubble Space Telescope. Now this James Webb Telescope is going to catch the IR part, that is infrared part of the electromagnetic spectrum. So here same thing is displayed in a different way. So this is infrared part of the electromagnetic spectrum, and JWST is designed for that. Now this infrared we are using in our everyday life. These are basically heat waves, and we use those in electrical room heaters, cookers, then TV and remote controls. So we are doing surfing on TV by using infrared waves. Optical fiber, nowadays we have got internet connection through optical fiber. So there also IR is used in security system, night vision cameras, then IR lamp for patients. So that is a use for treatment also. So we are using IR at many places in our everyday life. So why IR is used? See, this shows us a photograph of a Carina Nebula. Now, what is a nebula? Nebula is a region in space where stars are taking birth. So it is some nebula in space, and this photograph was taken in visible camera. This photograph shows us visible camera, or a photograph taken from visible camera, while this one is the IR photograph. So you can obviously see the details. Many more stars are visible in infrared. So that is why we want to go to infrared telescope. This is one more photograph of the Eagle Nebula. So this is in visible and this is in infrared. Naturally, you said that infrared gives us many more details of these celestial objects. So why we are using infrared? The waves which we received from old and distant objects are in IR. So we are receiving the waves in IR. So not in visible part of the spectrum, but in IR. Then the objects which are cold, like debris, then planetary disks and planets, they are also giving out IR all the time, and we want to receive those on the Earth. Then IR is actually absorbed in Earth's atmosphere. That is why the telescope has to be kept outside the Earth's atmosphere. So IR, that is a property of the atmosphere of the Earth, that IR gets absorbed, and therefore IR cannot reach the Earth's surface, and hence a space telescope is required. What happens with existing space telescope, for example, say Hubble telescope, that they themselves are emitting IR radiation. See, there is a principle in physics that all objects, including you and me, all objects are emitting IR, infrared waves, at all temperatures except absolute zero. So all of us are giving out IR. Every object in this universe is giving out IR, which has got temperature higher than the absolute zero, and most of the objects have got that temperature. So these existing telescopes themselves are radiating in IR. Naturally, they cannot take readings of IR coming from space, because the waves which are emitted by themselves will get mixed into the space signal, and we won't get the correct. So because of this fact, we can observe faint objects like planets, satellites, comets, asteroids, and Kuiper belt objects. Then, with the help of Webb telescope, we can observe some unplanned targets.
त्याचा फोटो मोठा करू शकतो का?
Hello, no. This is maximum.
Okay.
So we can observe unplanned targets like within short notice, like supernova expansion, explosion, and gamma ray explosions. Then I told you that it is successor to the Hubble Space Telescope. So compared to Hubble Space Telescope, Webb is having 5 times more light collecting area, then 100 times more sensitive it is. Its weight is half, 50%, and it is designed to cover the entire IR range, infrared range. So this is the photograph of Hubble Space Telescope, which is in space since last 32 years, and it has sent us such a huge information, such a huge data, that our knowledge of the universe has totally changed due to Hubble Space Telescope. But now we are having more powerful telescope in the form of JWST. See, this is the primary mirror of Hubble telescope, while this is the primary mirror of the Webb telescope, which is made up of 18 segments. See, mirror diameter is a primary specification of any telescope. So larger the mirror, more light it collects, and therefore better is the efficiency of that particular telescope. So now let us have some photographs when Webb telescope was made. So some of these photographs in the video clip that you have seen at the beginning. So now this is the complete primary mirror. It is called as primary mirror, or it is called as objective mirror, because light coming from the object in space falls on this mirror first, and then it gets reflected and it falls on other mirror called as the secondary mirror. So here the yellow color mirror that you are observing is the primary mirror, and here the secondary mirror is situated here. So the IR is incident on this primary mirror, and those are getting reflected and concentrated on the secondary mirror, which is situated here. So this is the sun shield, because we don't want any sunlight to fall on the telescope, because that will hit the telescope and the telescope itself will start emitting IR. So what we want zero IR to be emitted by the telescope. So this is the sun shield. Now this photograph tells us how the sun shield is working. See, this is the total telescope, entire telescope, and this part is the sun shield, which is magnified over here. So sunlight is incident from here, from this side, suppose, as seen over here. The sun is shown here. So sunlight is incident. Part of that is reflected, part of that is transmitted, but that is also reflected. A fraction of that comes here, still fraction comes here, and a very small negligible fraction comes here, almost nothing. So see the temperatures. On the sun side, the temperature is 125 degrees Celsius. 125 degrees Celsius. While on the other side, the temperature has dropped to minus 235 degrees Celsius. Minus 235 degrees Celsius. This is incredibly low temperature. Very, very low temperature. So this is possible because of this 5-layer sun shield which is used in the telescope. Therefore, the temperature of the telescope will be in this range, minus 235 degrees and some closer value. So again, some photographs. See the complexity involved in making of the telescope. The hugeness. Again, this is primary mirror, secondary mirror here. This is the final model of the telescope as seen from the below. Again, a model was on display before it was launched. These are the engineers and scientists who have made this telescope. So it was launched in December last year. The total payload meaning scientific equipments, that mass was more than 6,000 kg. Primary mirror segment 18, I have shown you that. Diameter 6.5 meter. Then area of the primary mirror, that is IR collecting area, that is 25 square meter, quite a big area. Then the sun shield, which I have shown you, it is more than 3,000 square feet in area. And most incredible thing about the telescope is its distance from the Earth. It is a distance of 5 lakh kilometer. 5 lakh kilometer from Earth, and it is situated near a point called as Lagrangian 2 point, L2 point. About this I will talk later. Then mass duration is 5 to 10 years. The cost is also used, 10 billion US dollars. But the research that this telescope is going to do, the value is actually, it is invaluable, let me say. So the final stage before launching. So it is being taken to the launch pad. Now it is ready for the launch. Control room. So it is launched in space. Okay. So now see what happened immediately after the launch. So it was launched. Then first what happened? The solar array deployment was there. That is the solar array, which were there in the folded form. Those were unfolded. And all these operations, which now I'm going to tell you, happened in space without anybody sitting over there. So all these were programmed and controlled from the control station on the Earth. So initially the solar array was functional because the telescope has to receive energy, that is power for its functioning. Then communication antenna, that was deployed. Then third step was sun shield deployment. Then secondary mirror, then primary mirror, and after that it went to its destination. So all these processes took place in 29 days. So 29 days, all these processes were going on, and it was traveling to the destination point. Now let us see where it is exactly. So from the sun, the first planet is Mercury, as we know, then Venus and Earth. So distance between sun and Earth is 150 million kilometer. Million is 10 raised to 6. That is 6 zeros after 1. So 10 raised to 6 is 1 million. So the distance between Earth and the sun is 150 million kilometers. Then see here, Hubble Space Telescope is going around the Earth in this orbit which is just 570 kilometers above the Earth's surface. 570 kilometers above the Earth's surface. That is where the Hubble is orbiting the Earth. Then distance of the moon from the Earth is some 384,000 kilometers. And where is Webb? Webb is at this point L2, which is 1.5 million kilometers, that is 15 lakh kilometers from the Earth. So now the Webb telescope about which we are talking is 1.5 million kilometers from the Earth. So this is the diagram showing us all these points called as Lagrangian points. So Lagrange was a mathematician and he has calculated some points. There are 5 such points, and Webb telescope is here at point called as L2. So I will not go into the details of how these points are calculated and so on, but we will just remember that it has got some significance. This L2 point has got some importance, which I will tell you. Now see, again, sun is here, Earth, moon is going around the Earth, as we know. The Earth is going around the sun in this manner. So these arrows are telling us how the Earth is moving. And this Webb telescope, this is the L2 point. This Webb telescope is orbiting this point L2. It is orbiting this point L2 and it is moving with the Earth. The speed with which Earth is moving, with the same speed it is moving. And where is its sun shield? Its sun shield is on this side. So no light coming from the sun is directly falling on the telescope. No IR which is emitted by Earth and moon is falling directly on this telescope, because there is what is called as sun shield. Though it is called as sun shield, it is protecting this telescope from the radiations coming from Earth also and moon also. So what are the requirements for JWST? It must be kept under this temperature, minus 223 degrees Celsius. Now getting this temperature is a very difficult job. So getting this temperature and maintaining this temperature is a very difficult job, but scientists have achieved that. And as I have mentioned before, why this low temperature is required? Because we want this telescope to emit minimum or almost zero infrared radiations. And why that is required? Because those radiations should not interfere with this IR signal coming from space. So it becomes the noise for the signal. So we want to reduce this noise and to get a pure signal coming from the universe. So a large sun shield to block light and heat from sun, earth and moon, which I told you just now. Then this shielding is maintaining a stable temperature for the telescope, for the structures which are on the other side, dark side. And as I have told you, that critical to maintain temperature, also it is critical to maintain the alignment, precise alignment of the primary mirror segments. Then this it is orbiting around L2 because it want to avoid the shadow of Earth and Moon. Because when shadow is there, temperature will change. So we want to completely separate the telescope from the sun, earth and moon, and therefore it is moving around the point L2. It is orbiting the point L2. So a constant environment as far as temperature is concerned is maintained. So as I have told you that orbit around L2 is keeping all the three bodies on the same side of the spacecraft. Then which instruments are kept over there? There are 4 instruments. We will not go into details, but we'll just have the names of those: near infrared camera, spectrograph, then mid infrared instrument, and fine guidance centers. These are the 4 major instruments which are situated on a Webb telescope. So these are the photographs of all these 4 instruments. So this tells about details of this telescope. Like these instruments which I have shown you just now are situated here. So this science instrument module is kept over here. Then optical telescope equipment, so mirror, etc. are here. Then sun shield is here. Then solar array on this side. And earth pointing antenna is situated over here. You can see a small antenna, dish-like antenna is here. So what are the main goals of this telescope? So it is going to search the first galaxies which were found after the Big Bang. So as you might be knowing that it is accepted by almost all scientists that our universe came into existence when there was a big explosion. And that explosion took place about 13.82 billion years ago. 13.82 billion years ago. So at that time, Big Bang took place. The universe came into existence. There was number of changes were there, and evolution was there. So when the first galaxies were formed after Big Bang, that this telescope will try to find out. Then how these galaxies evolved. So what were the changes? What were the changes that took place during all these years, billions of years, that this telescope will try to understand. Then observation of formation of first stars. So how and when first stars were formed, that this telescope is trying to find out. Then study of formation of planetary systems around the stars. See, all these processes take thousands of years or millions of years, and we have still not understood how a planetary system is formed. There are some theories, but we don't have concrete information about planet formation, planetary system formation around stars. And therefore, we have got little knowledge about formation of our solar system also. So if we want to study our solar system, naturally we should study similar systems, planetary systems, which are existing in space. And therefore, this Webb telescope is going to focus on the formation of other planetary systems also. Then formation of first stars and galaxies. As I have told you, Big Bang took place 13.82 billion years ago. So earliest stars, the first stars about which I am talking, they were formed 100 to 180 million years after the Big Bang. 100 million years to 180 million years after the Big Bang. So this is the span which scientists have calculated. So during this span, the first stars were formed. Then first galaxies, when those were formed, so the calculation is about 270 million years after the Big Bang. So you can see here that stars were formed earlier and galaxies formed later. So first galaxies were formed about 270 million years after Big Bang. See, what is this diagram telling us, photograph telling us? See, here is the Big Bang taking place. And a triangular shape here, which shows us that universe is expanding. So universe is expanding, and that is why it is shown in triangular fashion. So here the Big Bang has taken place. And now see, what is plotted on this x-axis? It is age of the universe. This is age of the universe. And it is plotted in billions of years. Plotted in billions of years. And how those are plotted? See, with decreasing numbers. That is, this is 13.7 billion years. And this is 0 billion. So when we go from left to right, we are going in the past of the universe. When we are going from left to right, we are going in the past in the universe. So see, Hubble Space Telescope, HST, Hubble Space Telescope has seen up to this point in the past. Hubble Space Telescope has taken observations up to this point. Now what is this point? Let us come down. It is 1 billion years. 1 billion years after what? After Big Bang. So the Hubble Space Telescope has been successful to record the readings, to take the observations up to this point, and that point is 1 billion years after the Big Bang. What James Webb Telescope is going to do, it is going further deep in space and up to this point. So it will go up to this point, and what this point represents? 0.3 billion years. 0.3 billion years after Big Bang. Naturally, you can see, you can understand that James Webb Telescope is going further deep in the past of the universe. It is going deep in space, and therefore scientists are looking forward for the operation of JWST and the data which it will send on the Earth. So the mission goals further measure the physical and chemical properties of planetary systems, including our solar system, and investigate the potential for life in all these planetary systems. Now, this has been a matter of curiosity and research for a very long time, that whether life is existing on other planets or not. So far, we don't have any concrete evidence about life on other planets. But with the advent of this James Webb Telescope, scientists are hopeful that we will get some clue as far as the extraterrestrial life is concerned. So let us see what was the timeline of events for this telescope. Launch date, I have told you, December, 25th December. Then just 27 minutes after launch, it was released from the rocket upper stage. Then on 24th Jan, sun shield, mirrors and other components were fully unfolded So this is a miracle that has taken place for the first time in human history. That such sun shield, mirrors, and other components are getting unfolded, they are getting deployed automatically. That is, of course, automatically meaning all these events are programmed events. So this is a wonderful success that astronomers have got when this telescope was launched in space. Then the spacecraft entered at its in the orbit at its destination, which I told you, L2 point, and all instruments were powered off. So that happened on 24th Jan. On 3rd February, what it did, some testing was going on. So it detected first photons. Photons are particles of light or quanta of light. So those were detected. First quanta, first particle, light particles were detected on 3rd February. Then 11th February, almost completed first stage of alignment. So every segment of its primary mirror located, imaged, and centered the target. Some star was there. So it was focused. The primary mirror was focused towards a target star. It was a testing going on, so that the target star was some star was selected, and the primary mirror was taken into that direction. See, all of us have taken selfies many times, but this James Webb Telescope has also taken, the primary mirror has also taken its selfie. So this is primary mirror selfie, and this image was sent on that day. So what was the first image? See, the star was single, but you see many images of the stars. And if you count them, the images are 18 in number, 18. I have told you that the primary mirror has got 18 segments. So all those 18 segments have formed 18 images. Actually, only one image should be formed. It means that the primary mirror was not aligned at that time. So it was part of actually alignment. So slowly the alignment was done in such a way that all these 18 images merged into a single image. All these 18 images were merged into single images. So till that was achieved, the alignment of the 18 segments was done. So that made scientists understand that proper alignment of all the 18 segments has been done, and now the primary mirror will work as if it is a single mirror. Which tasks were completed? Cooling. See, cooling was a very important task, as I already explained to you. So that was completed. Then mirror alignment, focusing, final testing, and calibration. So all these important jobs were completed by this telescope as per the schedule. And now the telescope is all set to reveal the treasures of the universe. And NASA is going to release first full color images on 12th July. On 12th July, just 9 days from today. So we are meeting through this web meeting or Zoom, Google meeting at right time, because the first image is just 9 days away from us. So just to summarize, here it was launched, then sun shield deployment, mirror deployment, arrival at L2 at the desired point, then telescope cooling, telescope alignment, instrument calibration, and now first images and spectra. So now we are here. We are at the last step. We are at the last stage of the operation of this telescope. So all these primary adjustments have been done successfully as per the schedule, and now we are eagerly waiting for the first images and the spectra which this telescope is going to give us. So here I will stop. The photographs which you have seen in this program, so those images or photographs were taken from NASA website, then European Space Agency, Canadian Space Agency, then Hubble mission and Space Telescope Science Institute, which is monitoring the Hubble project in US. So I thank you all. I thank Prasad for inviting me, and thank you once again.